Okay, so let's talk about matrices. A definition to start with, a matrix is a rectangular array of numbers. So let's look at an example. Here's an example. Let's let A, capital A, be equal to the matrix with 2 rows and 3 columns. The first row is a 1, 7, and 5, so 3 entries, 3 columns. And the second row is square root of 2, 0, and a negative 1.2. Couple of things to notice here. Capital letters are usually used to denote a matrix. So let's say use capital letters for matrices. Another piece of notation to be aware of, matrices are usually denoted with these square brackets or parentheses. The straight up and down kind of absolute value sign, those will be used for something called a determinant, so you don't want to use those, but you do want to use either square brackets or parentheses. Now the size, let me move this up a little bit. The size of a matrix is given by M by N. Okay, so we're talking about the size, and the M refers to the number of rows, and the N refers to the number of columns. Okay, so for example, in our matrix A here, we could say the size of matrix A is 2 rows by 3 columns. So we pronounce this 2 by 3. Okay, so the way we'd read this is 2 by 3. We don't say 2 times 3 or anything like that. We say the size of A is 2 by 3. So let's do another example just to make sure we're comfortable with this. Let's look at matrix B, capital B for matrix, and we're going to have one big column here, and the entries in this column are going to be 1, 2, and pi. So we could say the size of B is, we can say B is 3 rows by 1 column. So B is a 3 by 1 matrix. Okay. You could also say that B is a column matrix or a column vector, because it consists of just 1 column. And similarly, you could imagine something that had just 1 row in it. So you could let matrix C, capital C, be a matrix defined by 1 row and 4 columns. We could go 0, 0.1, -5, and 10. And we would say C is a 1 by 4 matrix. And similarly, you could call it a row vector or a row matrix. Okay, other terms that we should be aware of, the elements in a matrix have a location. So the elements in a matrix have a location. Let's emphasize that, the location given by the row and column indices. So let's take a look at an example. Suppose we make a new matrix here. Let's call this matrix D. So matrix D will be 3 rows and 4 columns. So we'll go 1, 2, 3, 4 for our first row, 0, 0, -2, and 7, square root of 3, 0, 1, 4, and a -1, 0, 1, 5. Okay, So D is 4 rows. I think I said I wanted a 3 by 4. Let's get rid of a row here. Make it a little bit more interesting for us. Fix this up. There we go. 3 rows by 4 columns. That looks better. D is a 3 by 4 matrix. Great. Okay, so now let's talk about the position of number 7, of the element 7. So we could say 7 is in position or location. Well, where is it? It's in the second row, 4th column. So it's in location 2, 4. So this is second row, 4th column. Okay, great. The last thing we want to talk about is how to go between systems of equations and matrices. So we'll call this section how to convert a system of equations to something called an augmented matrix, and I'll define what we mean by that in a minute. An augmented matrix. Okay, how do we do this? Okay, so let's start off with a system of equations, and I'm going to start off with the 3 equations. So we're going to start off with the 3 times variable x sub 1, and I want to put that in a different color to emphasize a point I'm going to make, plus 2x2 minus 1 x sub 3 equals 4. Next equation, we'll have a 0 x1 plus 4x2 plus pi x sub 3, and that'll be equal to 0. And for our last equation, we will have a negative 1 x1 plus 5 x2, and let me be consistent with my coloring here. We keep the variables in black and the coefficients in purple. And our last coefficient here will be a 7 times x3, and that'll be equal to 1. So there's our system of equations. So let's label this system of equations. Linear system, to be more specific. And we want to write that as a matrix. And so since we have 3 equations, we will need 3 rows in our matrix. Now, the first 3 columns of the matrix will be the coefficients of our linear systems. And so this is called a coefficient matrix. And so reading off these coefficients, we have a 3, 2, negative 1, second row 0, 4, pi, and third row negative 1, 5, and 7. The other piece of information in this linear system are the constants over here. And those constants we will put in their own column 4, 0, and 1. So these are our constants. Together, the coefficient matrix with the column vector for constants, that makes up something called the augmented matrix. And throughout our course, we will be working with augmented matrices. We won't be working so much with systems of equations. We'll be converting everything to matrices and doing matrix algebra from there. All right, now as a different example, suppose somebody gave you the augmented matrix and wanted the system of equations. So let's look at an example. Suppose we want the linear system corresponding to the augmented matrix given below. I'll scroll this up a bit. And furthermore, let's just agree that we will use variables x1, x2, and x3. Okay, so here's our augmented matrix that somebody gives us. They give us the matrix 1, 2, 3, negative 1, 0, 5. And in this last row, A, B, 4, and the constants are 0, 1, and 6. So to write this as a linear system, keep in mind that our variables here are x1, x2, and x3. Our constants are over here in this column. So to write this as a linear system, we would write 1, getting right color here, 1x1 plus 2x2 plus 3x3, and that's equal to the constant of 0. The next row we would have a negative 1x1 plus 0x2 plus 5 times x3 equals 1. And the last row, this is just another coefficient, so it's just a times x1 plus b times x2, 4x3, and that's all equal to 6. Now you might be wondering, why did I even write down 0 times x2? And I agree that's a little bit redundant. We could exclude that. We don't have to write that down. And so we could just have negative x1 plus 5x3. Okay, so there is our linear system corresponding to the given augmented matrix.